Hello everyone, welcome to this lecture. Hope you've been enjoying learning the basic ideas and probability foundations from the lectures. This one is going to be slightly different from your usual examples that you've seen in this class. Many of our examples are with small probability spaces, simple sample spaces, etc. This one is going to be a slightly genuinely complex case, as in a lot of things can happen. There will be a sequencing, and then we will study a probability of a particular event that we are interested in. Okay, so it goes by various titles. Two very common titles for this problem. One is called Gambler's Ruin. Gambler is getting ruined, right? It sounds very dramatic. The other is probably a little bit more mundane. It's called a simple random walk, right? So both of these are names given to this setting, this probabilistic setting that we will look at. Let's get into it. So here's the setting. Let me describe that. I'll describe it in the gambler's term, in the situation where there's a gambler involved, but there's also the simple random walk which we can think about. I'll point that out as we go along. Okay. So let's imagine there's a gambler at a casino. He's got K units of money with him. Typically, if this problem is from the US or something, people would say dollars or some other currency. In India, we don't have too many casinos, except if you go to Goa or someplace like that. But let's just keep units of money, right? So that's common. Whoever you are, you understand what it is. The gambler has K units of money, and he's going to play a game at the casino. So this is a game which is very simple in some sense, but it's very illustrative of what can happen. Okay, so the gambler, if he has any money in his hand at all, any units of money in his hand at all, he's going to play this game, which is to toss a coin. So the game involves tossing of a coin, and if the coin shows up as heads, right? If it lands so that you see heads on top, then the gambler gets 1 unit of money. He gets 1 unit of money. The casino gives him 1 unit of money. Okay. On the other hand, if the coin toss results in a tails, then the gambler loses 1 unit of money. He has to give 1 unit of money back to the casino. Is that okay? So hopefully it's clear. So he starts with K units of money. The first toss, what will happen if it is heads? He will get 1 unit from the casino, so he gets K plus 1. If on the other hand, if the first toss was tails, he has to give 1 of his units to the casino. He gets K minus 1. So you can think of this, most casinos work with chips. I don't know if you've been to a casino. So they work with chips. You give some money, they give you chips. So these chips are like these units of money that we have. Okay, so that's the game. So now there's the two situation. When does the game stop, right? So when does it stop? What is the gambler's ambition? The gambler's ambition is to not lose all his money, of course, right? So that can happen. If the money at hand becomes 0, the game stops, right? The gambler has gone bankrupt. He has gotten ruined. Okay, so that's the gambler's ruin, and that's what is the event we're interested in. So that is one way the game will end, right? He has no money. He's finished. He's ruined. Okay. The other possibility is he achieves his goal. His goal is to get n units of money. Okay, whatever that n could be. So you can imagine n being slightly larger or much larger than k, right? So maybe he wants to buy something expensive. So he wants to convert his K units of money to capital N units of money. And if his money becomes capital N, then he will stop. So the gambler is, he wins out. He just takes all his chips, goes back and cashes the money, and he's happy. He goes out. Okay, so that's his success. It's winning. But the event we are interested in is this probability. The event is the gambler going bankrupt, the gambler being ruined, and P sub K. Okay, so clearly this probability will depend on K, it will depend on N, it will depend on various things, isn't it? So it depends on the situation. But we will just call it P sub K. The N dependence on N is sort of implicit, so we won't put it out very clearly. So of course, it will also depend on the probability of heads and probability of tails. We haven't come to that yet. So we'll just call it P sub K. It's just notation. The probability that the gambler goes bankrupt is P sub K. Okay. So you've learnt enough probability now. You can imagine the probability space here, right? So what are the outcomes? The outcomes could be, heads, tails, heads, tails, heads, tails, over combination. At no point should the total number of amount of money he's lost, it should not go to 0. The money should not go to n. You can feel the complexity of the space. If you were to write down all the outcomes and worry about the probabilities here, there, even if you know the probability of head, even if you know the probability of tails, even if the coin is fair, it feels like a difficult problem. How do you know what are all the cases in which the gambler is going to go bankrupt? How do you enumerate all of that? How do you find probability for each outcome, add it up? It seems quite a bit complicated, doesn't it? So it turns out there are very interesting ways of solving such problems, right? So, and conditioning, the simple act of conditioning plays a crucial role in these things. So by conditioning on something, you observe that the next step is very similar to the previous step, right? So he has k units of money, something can happen in the first toss, and then after that he's in the similar situation, isn't it? Right? He has maybe a different amount of money with him. It could be k plus 1 or k minus 1, but after that the game has not changed. It's the same game, right? His money has changed, but it's the same game. So you have this, after one event, after one action from you, right? After one play of the game, one toss of the coin, you see that the subsequent step is very similar to the previous one, okay, except for this amount of money that has changed, okay. So you can exploit this and solve this problem using a nice recursive equation type definition. So let's see that in the next slide. Okay, so the main idea, like I said, is to condition on the first toss. Okay, so we'll use some notation just to simplify our work. You'll see that the final equation is very simple. We will write it once again later also, but let's just focus and go through the steps here. Okay, so I'll use this notation A. A is the event that the gambler goes bankrupt, the gambler is ruined, and I know that this PK is actually, I will call it as capital PK of A, just to give it a little bit more, connection to the event A, etc. It's basically the probability of gambler going bankrupt starting with k units. He has k units in his hand, he starts playing the game. What is the probability he'll go bankrupt? That is P sub k or Pk of A. Okay, so it's just nice to write it like this so that it seems clear as to what's going to happen. We'll quickly go back to the Pk. It's all the same, except that we write it a bit differently. Okay. The next event is the first toss. I'm going to condition on that, so let me give it a name, right? So this event B is the event that the first toss is heads, right? So the toss of the first coin is heads. Okay, that's B. Now let's condition on B, right? The first toss could be B or B complement, right? So it could be heads or tails. So we can condition A on B and use the law of total probability to write Pk of A as P of B times probability of bankruptcy given B, right, plus P of B complement times probability of bankruptcy given B complement. Okay, so that's the important step. It's a very simple step, but we've gone to another conditional probability space, right? In the first event, when B happens, we go to the conditional probability space of given B, right? We go into the world has shrunk a little bit, right? The first toss has become B. So we go into that different probability space, which is the conditional space, and that probability that we need to evaluate there is probability of bankruptcy given B. Likewise, we do for B complement. Since B and B complement are disjoint, you can add the two probabilities plus probability of B complement times probability of bankruptcy given B complement. So now that probability space is different, isn't it? Probability of bankruptcy given B complement is conditioned on another event B complement, so that changes the probability space. Now the crucial point is the next bullet point that I've written here. Okay, in this conditional space, given that the first toss became heads, what happens? The first toss is heads. The casino has given 1 unit of money to the gambler. So the gambler now has k plus 1 units of money, right? Now with k plus 1 units of money, if you place the game, what is the probability he is going to go bankrupt? So that is your conditional space, isn't it? So that's the probability of bankruptcy given B. Now I already have a notation for this, isn't it? Pk of A is the probability of bankruptcy given you have k units of money with you. When you have k plus 1 units of money with you, it is simply Pk plus 1 of A. That's just sort of a notation, but you see how the probability spaces are connected. The one that you started with k, now you're starting with k plus 1. That's the new space when you condition on the first toss, right? Now the same thing happens with B complement. On the other hand, in B complement, the gambler gives 1 unit of money to the casino. So he's lost a unit of money. So his amount of money now is k minus 1. So the conditional space is such that probability of bankruptcy given B complement is going to be Pk minus 1 of A. Okay, so that identification that the conditional spaces are related to k, this k controls everything, right? So in one conditioning it becomes k plus 1, in the other conditioning it goes to k minus 1. So it's like a simple equation connecting pk, pk plus 1 and pk minus 1. Okay, and what is that equation? It's the same equation written again here. Pk is probability of heads times pk plus 1 plus probability of tails times pk minus 1. So hopefully you can see that here. So you can see that this equation, pk of A being equal to p of B, probability of bankruptcy given B, plus p of B complement, probability of bankruptcy given B complement, the same thing I have written again here, except that pk of A I have written as small pk, probability of bankruptcy given B, which I know is pk plus 1 of A, I have written as pk plus 1, and then probability of bankruptcy given B complement, this is pk minus 1 of A, I have written it as pk minus 1, small pk minus 1. So probability of heads times pk plus 1 plus probability of tails times pk minus 1. So these equations are called difference equations. It's sort of like a recursion, pk depends on pk plus 1 and pk minus 1. Okay. So how do you solve these equations? Is there a way to solve these equations? It turns out there are systematic ways to do it, but for this particular problem, we can sort of write it in a way and solve it. Okay, so it's all a question of solving it. So worst case, you can numerically solve it, right? So 0, n. So okay, the initial conditions are very important. So let's write down the initial conditions. P0 is equal to 1. So what is P0? I mean, if you think about it, it's the probability of gambler getting ruined if he has 0 money to start with, right? There's no money, so he's already ruined. So P0 is 1. Okay, and the other condition which is interesting is this Pn. Okay. Pn is what? If he has got n units of money, there's no chance of him going bankrupt. Why? He just stops playing at that time, isn't it? So Pn equals 0. So these are called boundary conditions. Okay, these boundary conditions are very important. Whenever you have an equation like this, you need such boundary conditions to solve them. If you don't have a boundary condition, you won't be able to solve. Okay, so you need two conditions like this. You have an equation like this, and then you are done. Okay, so these conditions are also called absorbing barriers in some sense, because when it reaches that, the game stops, right? So it doesn't continue after that. Either at n or at 0, the event has happened differently, right? If he reaches n, the event has not happened, he's not gotten ruined. If he reaches 0, then the event has happened, the gambler has gotten ruined. But these both are absorbing barriers in the sense that they just absorb the game, right? So it's finished, the game is over at that point. Okay, so this is the equation that we need to solve. If you can solve this equation, you're done, right? So notice how we started with quite a complicated looking probability space setting, and we broke it down just by conditioning on the first toss. That simple matter of conditioning on the first toss gave us this fantastic equation. Okay, so that's nice. So let's move on to the next slide. Okay, so the next slide, I will show you two solutions for the difference equation. It's not so critical that you understand how we solved it. The main idea is, I'll quickly show you how I solved it. I won't spend too much time on this, but let me just focus on the result. If the probability of heads and probability of tails is half, it was a fair game, right? If it was a fair game, then it turns out the probability of ruin is 1 minus k by n. Okay, so 1 minus k by n is the probability that the person will get ruined. Okay, so that's the number to remember. So for instance, if k were to be, say, 3n by 4. Okay, so if you had 75% of the money, then probability of failure is only 1 by 4, 0.25. So on the other hand, if you have only 1/10 of the money or something, then your probability of failure is very, very high. So it sort of tells you what you can expect, isn't it? So it sort of tells you in most cases you'll be okay if you have already a lot of money to start with. Okay, so the amount of money you can hope to increase with this kind of a fair game is quite less. Okay, so this is the probability of ruin. It's 1 minus k by n for a fair coin. So how did we get there? You can see quickly, probability of heads and probability of tails is half. So I wrote pk is half of pk plus 1 plus half of pk minus 1. You can rewrite this in a clever way. It's basically pk plus 1 minus pk equals pk minus pk minus 1. Okay, so that's what this means. It's just rewritten that way. I can let this difference be d. And notice this difference stays the same irrespective of k, right? As you keep changing k, this difference remains the same. So you exploit that and you can quickly write Pn in terms of d. Okay, so you will get Pn to be nd plus 1. and what is Pn? I know is 0. So from there you can find d. D is minus 1 by n. So you can see how the initial conditions play a role, the boundary conditions play a role in determining what this d is, and you get Pk to be 1 minus k by n. Okay, so that's a fair coin. So most of you who know who've been gambling, you'll know it's never fair, isn't it? It's always there's an advantage to the casino. So supposing in the general case you say probability of heads is P and probability of tails is Q. Notice the final answer Pk after you solve all these things works out to something like this. Maybe I should. So let's see the final answer. I'll just quickly walk you through the derivation later on, but the final answer is also equally important. You see that Pk, the probability of ruin, is a fraction. What is in the denominator is 1 minus q by p power n. Okay, so that's what is in the denominator. Q is the probability of tails, p is the probability of heads, right? So q by p is sort of like represents the unfairness. So how much more probable it is to be tails over heads, right? So even if it is a little bit, you raise it to the power n, so 1 minus q by p power n is in the denominator. In the numerator, you have q by p power k minus q by p power n. So that's what you have in the numerator. So there is like a exponential sort of dependence with k, right? The moment you have a little bit of unfairness. So let's say even if q is 0.6 and p is 0.5, you can see how quickly it will, it'll become very small. So you can't really hope to make any kind of money if q is larger than p. Okay, so this is the final answer. If q and p are not equal, how did I derive this? This slide has the details. You write the same difference equation, but then you can't say it's equal. There'll be a fraction q by p that's showing up here, right? Pk plus 1 minus pk will be q by p times pk minus 1, and you use it, unravel it to the end. And then once again, you can write pn in terms of q, p, and n, and you get d, and then substitute it back, you will get pk. Okay, so it's the same method. You write the difference equation, that's very important, and then use the boundary conditions and try to solve for whatever probability you want. Okay, so what's been asked here is the probability of ruin. You can also calculate other probabilities. You can let pk be other things or related things, and you can calculate some other probability. So I believe one of your assignment questions may be on that. If you have, if you're able to do that, then it means you understood this trick of how the first conditioning helps you in understanding probability of ruin in the gambler's ruin. Okay, now why is this called a simple random walk? You can imagine somebody standing at a point and he tosses a coin and decides whether to go right by one step or left by one step. Okay, so it's also called a drunken walk, or various names are there. So with some probability you take a step to the right, some probability you take a step to the left. Okay, this is called a random walk. Okay, you don't know where you're going, you want to keep walking, that's all, but it's just random. So at every point you toss a coin again. With heads you take a step to the right, if it's tails you take a step to the left. Okay, so you are at some point k. Okay, this gambler's ruin is sort of asking you what's the probability that you will get to 0. Okay, and n is like the end of the road. You can't cross n. If you get to n, you like fall off the road or something to the other side. So if you get to n, you're done. Before getting to n, when will you get to? What's the chance that you'll get to 0? Okay, so that's the gambler's ruin question, isn't it? So that's the simple random walk interpretation of gambler's ruin. Okay, so that's the end of this short lecture on gambler's ruin or simple random walk. Hope it was interesting to you, and hope this gives you enough background to solve the problem that's coming up in the assignment. Okay, thank you very much.